Today we're going to take a look at section 3.4. So back in 3.2, we talked about models for addition and subtraction. Shake your head if you remember what I'm talking about. Yep, good. And then we moved on into multiplication and division in section 3.3, but we are returning now to addition and subtraction. And what we're going to be looking for at the beginning of this section anyway is algorithms. Now, algorithms just means ways of doing something. So this is one of those sections where people will sometimes get frustrated. I don't think they're really frustrated at me. They're mostly frustrated because they know how to add and subtract. They were taught one way and only one way, and it made sense to them, and they know how to do it, so why learn something else? The reality is that there are a lot of kids who don't do very well with standard algorithms, standard ways of adding and subtracting. And so when you hear parents get really frustrated because they can't help their kids, it's usually because some teacher's doing something like this. They're trying to help kids learn and understand a different way of doing it because not everybody learns and thinks the same. So, most of these I have seen versions of come home on my kids' work from schools, so you really are going to see them in your curriculums when you're out in the schools observing, when you're doing your student teaching, and then ultimately when you're actually teaching in your own classrooms. So my goal is not necessarily to make you decide that I absolutely love a method that I didn't learn to begin with, but it's to help you understand that there's other things that are available to help your kids, and so that when you get out there and you're seeing some method, and it maybe even won't be one of them that I've shown you, you don't feel quite so blindsided that there's other ways of doing math than the way you learned, okay? So we're going to start with the concrete model. This one is going to be familiar to you. Whether you've done it recently or not, it's not the point, but you've seen this one before, I'll guarantee it. So I brought in base 10 blocks, the red blocks. Remember that the other day? The concrete model has children take those kinds of blocks and form other numbers with them by taking two numbers and combining them. So when you're dealing with the concrete model, this is 34, so you end up with 3 longs, right? So a child would do this in physical form, not drawing it out like we are. Okay, they're gonna have 3 longs, 3 of those long red pieces, and they would have 4 individual units. And this would be one of their numbers. This would be the number 34. So you give them, hey, create me blocks for 34, and they would put them all together, and this is the picture they'd have on their desk, okay? And then you say, okay, now create another stack of blocks that's 18. And they would create for you 1 long, and then they would have 8 individual units. As you can tell, I don't draw very well, so my individual units don't look very uniform, but you can pretend like they are. Like this. So I've got 34 in one diagram. I've got 18, in the other diagram over here. And now you're telling the kids to sort of mush them all together, combine the things that can be combined, and see what they have when they're done. Well, again, if they're more like Lego style, the ones I have are not perfect like Lego style. They don't snap together, but the ones that do snap together are really nice because they can snap together how many of the little units? 10 of them. And if they snap together 10 units, because we're in base 10, they will have a long. So if they take all 8 of these and 2 more of these, they push them together in a long format, they will have a 10 long. And now how many longs do they have? Well, they started out with 3 in the first set. They have 1 in the second set. And they piece together 10 more individual little units, so they have another long. And how many individual blocks do they have left after that? 2. And then when they go back to count up what they have, they can count very quickly to say, oh, look, I have 5 longs and 2 units for the number 52. Make sense? You could do this with coins as well, right? Coins would be a concrete model. You use dimes and you use pennies, especially for children who do, in fact, understand money to some degree, right? So we can take 10 of our pennies and we can exchange them in for a dime. Or if you wanted to use dimes and dollars, that's even got a really nice visual, right? Because the dollar is actually bigger. Kids get really tripped up on coins because our dime's smaller than our pennies. Y'all know what I'm talking about, right? So it's really hard to think about it being a bigger value. But if you did dimes and dollar bills, it would work really well. 10 dimes would equal a dollar bill, and you could trade them in for $1. And kids definitely understand that they like dollars better than coins, so that part works nicely too. Okay, so this is a block version of a concrete model. You could also use a coin version of a concrete model would be appropriate. Okay, so this is concrete. Standard algorithm, the one that you know and at least have come to appreciate the most, is this concrete model, or the standard model, excuse me. And so in the standard model, you do something like this. There's some very strange things that we do with our standard model that you don't even think of as strange anymore. Strange thing number one, what do you add together first? The 4 and the 8. And that means you're actually adding from right to left. And that's strange. Why? Because we read from left to right. All right? So that's a little awkward. That's just something we do backwards, and that feels a little bit funny. Now, there's reasons we do it, but the fact is that it is a little awkward. So we say, okay, 4 plus 8 is 12. And some children want to do this. Right? But we say, no, you can't do that. What do you have to do? You write the 2 down, and you, sort of old-fashioned language is the word carry. That's what I learned as well. You don't hear carry used very much anymore. You hear regroup. So why are you doing that? What's really going on? Well, if you're teaching this method, you should be explaining what's going on. So there's some meaning behind it. So what is the point? Why did we move or carry or put this 1 in the next column? Yeah, because when we got the number 12, the 12 is 1 10, so now it's in the tens column, and 2 1s that get put in the ones column. Are you with me? Okay, that's what's happening there. And then we say, okay, let's move over now to the tens column, and we're going to add all our numbers together. 1 plus 3 plus 1 is 5, so I have 52. So one of the nice things about this method is it's very efficient, right? That concrete model picture, if I had to draw a picture every time, it would just kill me. It takes a while, right? It's great for conceptual understanding, but it is not efficient. Right? Efficient means it happens quickly, or it's able to be done quickly. The standard algorithm, it's quick. It's efficient. It's a little awkward in this left to right business. Got this funny carrying, regrouping thing going on that's a little awkward. It's even more awkward when we get to multiplication, as I'll show you on Friday or Monday after spring break. The expanded algorithm gives a little bit less efficiency, right? It's going to be a little bit slower, but a little bit more intuitiveness of what's happening than the standard algorithm, but it's very related. So let me show you how the expanded algorithm works. The expanded algorithm is emphasizing what the numbers in the placeholders they are, actually what value they hold. So when I see 34, I recognize it as 30 and 4. Because that's really what 34 is, right? Or you could recognize it as 3 10s and 4 1s. Every time I teach this, I can't decide which one I like better. They both have some benefit to them. And then my 18 is a 10 and an 8. Or you could recognize it as 1 10 and 8 1s. I don't care which of these ones you use. They're both the expanded algorithm, okay? The nice thing about thinking about it like this is that it doesn't really matter if we start on the left or the right. So I can add together very much that 30 plus 10 is 40, and 4 plus 8 is 12. Or I can add that 3 10s and 1 10 is 4 10s, and 4 1s and 8 1s is 12 1s. Okay, so I get the nice sort of moving from left to right, which is rather friendly. I still end up with the problem, of course, that I have 40 and 12. So 40 is 40 plus, and then 12 is a 10 and 2. So I'm breaking it apart again. 40 and 10, that's 50. So I have 52. Over here, 4 10s, I have 4 10s, and then 12 is 1 10 and 2 1s. So these two pieces give me 5 10s and 2 1s for the 52. So it's kind of like you're working with the concrete model and the standard algorithm sort of playing into each other a little bit. It's called the expanded algorithm. So if you were using this in a classroom, just like if you were using the concrete model in the classroom, what I would see most likely is that you're using this at the front end, right? You're using this to explain what's going on behind the standard algorithm, or we'll get to a couple more here in a minute. But you're not doing this forever. I'm not drawing concrete pictures. I'm not playing with blocks forever. But to get a conceptual understanding of what's actually happening, it's really good.
I have a question.
Yes.
On the right side,
Mm-hmm.
you did 3 plus 1, and then 4 plus 8. But for the 10 and the 10 and the 1 and the 1, wouldn't that be kind of confusing? Or is that you just bring it down?
Sorry, you're bringing it down. So you have 3 tenths. Think of it if you were working with like dollar bills, right? So if I had $10 bills and $1 bills, and if I had 3 $10 bills and I have one more $10 bill, that's 4 $10 bills. So the times 10 part is times the place value. So again, if you wanted to do it along with the long blocks, or if you wanted to do it along with $10 bills and $1 bills, you could get a better sense of what's going on there.
The place value.
Exactly.
Okay.
Yeah. But I understand what you're saying, where it looks like the 10 gets repeated, and why are we adding these and not these together? And that's a valid point. You'd have to emphasize what you're actually meaning by it for sure. Yeah. Okay, let me show you another one. This one is called the left to right algorithm. So I've got the numbers, and I'm gonna, for the most part, I'm stacking my numbers on top of each other as I'm talking about them. And you do work from left to right. And as you're working in one place value at a time. That's my leftmost place value. So 1 plus 3 would be 4. Oops, changed my pen. And this is 4,000. So in a very real sense, what I'm doing is I'm adding the 1,000 and the 3,000 together on that step. Okay, I'm ignoring all the rest of it. I'm just adding that, in this case, the thousands placed together. And then I move over and I do the same thing. I have the 5 and the 2. So that would be 7. So I have 700. And again, that's because I'm really looking at 500 and 200. Move over again, 3 and 1. So that's 4, and that's 40. So this is 30 plus 10, right? And then in the ones place, I have 4 plus 8, and 4 plus 8 would be 12. My numbers don't really line up very well. I'm writing smaller as I go. Okay, so I have 12. So I have 12 would be a 2 and a 1, and I have 2 place values it's taking up because there's 2 numbers. All right, so at the very end I had 4 plus 8. And because I've isolated place value holders, you can add straight down again. So this is 4, 7, 5, and 2. So you're really isolating one place value at a time as you're adding. No need to regroup because at the very end I add all the pieces together anyway. Okay? All right, lattice algorithm. We're going to have a lattice algorithm for multiplication. We have the lattice algorithm right here for addition. They do a really nice job of hiding the regrouping that's happening. And so I don't mean hiding as in it's a bad thing, but as in it lines things up really nicely so you don't have to feel the regrouping quite happening the same way. So let me show you how it works. Again, we line it up vertically, right? 1,894 plus 3,218. And you draw underneath it a rectangle. And however many place values you have, you need to split that rectangle into that many boxes. So this is 4 place values. So I need 4 boxes underneath it. Okay? And then to create the lattice part, you're going to divide all of your boxes in half from the bottom left to the top right. That's the grid that's created. Okay, again, doesn't matter if you move left to right or right to left. It makes no difference, so that's kind of friendly. And whatever you get, if you get a 2-digit number, then you use the top corner and the bottom corner. If you get a 1-digit number, you just use the bottom corner. So I'm just going to move left to right because I can. 1 plus 3 is 4, so the 4 goes in the bottom corner. Let's see, 8 plus 2 is 10, right? So that's a 1 and a 0. Top corner, bottom corner. Let's see, 9 plus 1, another 10. And then 8 plus 4, or 4 plus 8 is 12. So it looks like this. Okay, everybody good so far? So this is my grid, my lattice that's filled in. You do have to add in the next step from right to left. So there is sort of a drawback in that. And I'm going to sort of just extend my lines to show you what's happening, because we're now going to add along the diagonals. All right, so my bottom one, I've got a 2. We're just adding the 2 boxes together that occur in each diagonal. This is 1 plus 0, so it's 1. I have 1 plus 0, so it's 1. And I have 1 plus 4, so it's 5. Okay. Why is that happening? Well, what's really happening, truly, is that those carried numbers, the number when I did 12 that I would have carried, is in this top box, right? It's change of color here. It's right here. This 1 got carried, and it's applying to the next place value over, but we're doing it all in sort of 2 separate steps. So there isn't any regrouping. It's there, it's just hiding. All right? So it keeps the structure just a little bit different. Ready for my favorite? The next one is my favorite. It's called Scratch Algorithm. Okay, Scratch Algorithm. I want you to write yourself a note. This is really only practical if you're adding several numbers together. I don't mean big numbers. Like adding 1894 and 3218 with Scratch would be pointless. It could be a waste of time. It doesn't help you at all. But you'll notice that I created this problem on purpose. Are you good, Colton?
Yeah.
Okay. You'll notice that I created this problem on purpose where it has several numbers being added. That's unique. I didn't have that on any of the other problems. Are you with me? So we're going to add 34, 18, 69, and 87. I'm going to write them lengthwise as well, just on top of each other. So 34, 18, 69, and 87. Okay, we're adding from top to bottom, and we're using the right-hand column just like you would use standard algorithm. Okay, this is similar to standard algorithm. So when you're using the standard algorithm, if kids have done a good job with learning their addition tables, they're really good at adding 1-digit plus 1-digit numbers together. So 4 plus 8 shouldn't be a problem. The problem with longer lists of numbers comes in with after I do 4 plus 8 and I get 12, then I have to add 12 plus 9. And that I might not know because I may not have learned up to 12 additions, right? My plus 12s is. I didn't learn plus 12s. My kids learn multiplication with 12s. I don't know why. But that seems to be really popular right now. But not with addition still. Okay? So instead, what do they do when they get to 12 plus 9? They usually start working on their fingers. All right? And that's not terribly efficient. So let me show you what this algorithm looks like. When I get 4 plus 8 and I get 12, I scratch out the 8. And the reason that I do is because I've exceeded 1 digit. I have now a 2-digit number. So I'm making a slash mark that says I'm ignoring the fact that I had a 12, and I'm only going to remember the 2. Okay, so there was a 12, 1 and 2 here, and I'm going to ignore the 1, and I'm just going to remember the 2. Because 2 plus 9 is, again, an addition that I know. What's 2 plus 9? 11. So again, with 11, that's a 2-digit number, so I'm going to scratch. I had 1 and 1, 11. I'm going to forget the tens digit and remember the 1 and the 11 in the ones place. And 1 plus 7 is 8. And I write down the 8. And what I do is I go back and I count the scratches. Because when I scratched, what I did is I stopped counting how many I had in the tens place. Are you with me? I stopped saying 12 and I started saying 2. I stopped saying 11 and I started saying 1. So every time I scratched, I stopped the tens place. And I did it twice, which means there's really 28 when I got to the bottom of that column. 2 scratches for 20 and the 8 that I wrote down. So I'm going to carry my 2. And I'm going to start again. Top of the column, 2. 2 plus 3 is 5. That's great. 5 plus 1 is 6. No problem. 6 plus 6 is 12. That's too big. So I'm going to scratch 12. I forget the tens digit and I remember the 2. 2 plus 8 is 10. So I would actually scratch again. And I would again forget the tens digit, the 1, and I would write down the 0 because 10 is 1 10 and 0 ones. How many scratches did I make? 2 of them. So again, I would carry that over. I know there's nothing in my hundreds column, but pretend for a moment there were. And then I would add straight up my hundreds column, and there's a 2 in that column. So I have 208. Scratch addition takes a few times to practice it to get used to it, but it's super helpful because it actually speeds things up. So in terms of that efficiency that you loved so much in the standard algorithm, and you're like, she's messing with my efficiency, this is a really efficient method. But anything efficient takes a couple times to practice before you're going to be like in love with it, okay? And you still may not like it, but it is an efficient method. All right, any questions with the last one we did here, scratch addition? Okay, we're going to move into some subtraction algorithms next. Okay, many of the subtraction algorithms are going to look like the addition algorithms we've already done. The first one is the concrete model. So with the concrete model, we started by writing out what the number 34 looked like. So I had 3 longs, and I had 4 units, right? Looks something like this. All right, so one of the ways that we think about subtraction is we think about it in this sort of phrase as takeaway. I have something, and then I'm going to remove something from it. All right, so imagine I have 34 in concrete model right here, and I want to remove 18. What would removing 18 entail? What would I actually physically be taking away? Okay, what would we want to take away? 1 long and 8 units, 8 of the individual units. Okay, so everybody with me on that? Okay, so good job. Yeah, I want to take away 1 long and 8 units, but as you're sort of looking at it and thinking, there aren't 8 units there, right? I really only have 4 of them. So I want to take away 1 long and 8 units. What am I going to have to do to make that happen?
Break up one of the longs.
I'm going to break up one of the longs, exactly. So I'm going to change what's here into 2 longs, right? And then the third long will now be individual units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, definitely not to scale. And then I still have the same 4 I had before, right? Oh, 1 more. There we go. Look good? I mean, not good, but reasonable, understandable. Good. All right, and then the goal, like we said, was to remove 1 long. So if you were working with a child with actual blocks, you'd just take it away. I got to figure that out, so I'm just going to draw a scribble on top of it. And 8 of the units, right? So maybe you take the first 4 units that you already had, it doesn't really matter, and then you need 4 more. And the question is, after I've removed all those pieces, what remain? So what does remain? Well, I still have 1 long. And I have 6 units for the number what? 16. And the nice thing that happened, and you really weren't probably super aware of it when you did it, is you regrouped. You took a long that was 10 long, and you broke it into 10 individual units. You borrowed. That's what you really did. You borrowed something in a physical form. And if your kids have practiced that in physical form, it leads into talking about it in a standard algorithm really nicely, because they can see why when I borrow, it's getting bigger. Why am I allowed to now have a 2-digit number in a 1-digit placeholder? What's going on there? So the standard algorithm, as you well know, is doing just that very same thing, but it's sort of hiding. I say, kind of like you guys did, there's 8 units that I'm supposed to take away, and in the units place, the ones place, there aren't 8 to take them away from. I only have 4. I don't have enough. So I have to regroup, or I have to borrow. I have to take the 3 and I have to make that 2. And when the 3 becomes the 2 and I move it into the 1's place, it actually represents 10 units. And 10 units plus the 4 that are already there means there's 14 units now in the 1's place. And I can actually subtract. So 14 minus my 8 would be 6. 2 minus my 1 would be 1. Right? We don't think about it. We just move things, right? We just do it. But there's got to be a reason behind what we're doing, or it's not something you're going to be able to explain to a child very well. It's going to be really tough for you. So if I think about it sort of as a merging of that concrete model with the standard algorithm, we can look at the expanded algorithm the same way that we did a moment ago for addition. So the number that was 34 is actually 3. Well, I'll do it this way. I mentioned this before. 30 plus 4. And I have 18. Oops. So I have 10 and 8, and I'm trying to take them both away. Well, I mean, no problem taking 10 away from 30, but there's a problem taking 8 away from 4. There's not enough there, right? So what do we have to do? Well, I mean, we could actually take away 30 minus 10 if you wish. There's nothing wrong with that. But I wouldn't be able to continue the problem. I mean, not as it's set up. I'd have to do some kind of regrouping to make that work. So what you can do here is instead of taking 3, I have 30 that I'm changing into 20. And the other 10 that I'm removing have to go somewhere, so they go to the 4. And it's really clear why 3 became 2, but 4 became 14, because it didn't really happen that way, right? 30 really became 20, and 4 became 14. I just shifted 10 of them. But I see it better here, because I actually saw 10 move, not a 1 move and become a 10, which is a little weird. We can subtract. So I have 20 minus 10 here now, and I have 10. I have 14 minus 8, so that would be 6, and this would be the number 16. Or if you do this with the tens version, so you'd have 3 tens and 4 ones, and you're taking away 1 10, and you're supposed to be taking away 8 ones, but you don't have enough. So if you take 3 tens down to 2 tens, and then this 4 becomes 14, I think it's a little more hidden, sort of like it was in the standard algorithm, but one of those tens became 10 ones in this version. So again, we have 1 10, and we have 6 ones for 16. Yeah?
Are we supposed to do both of them?
No, you can pick which one of them, but they're both considered expanded algorithms. I just want you to see that there's a couple of ways that you might see them show up in a textbook if you were teaching from it. Yeah. If I have to be honest, I like this one better. It's my preference. I think it's a little clearer as to what's really going on, and it's easier to see and explain. But both of them actually show up in different versions of current curriculum. Okay, one more algorithm. So it's called equal additions. And I want you to write in big, bold, highlighted, red, blue, something to catch your attention. That the whole goal of this algorithm is no borrowing. Okay, this is like super important. Red flag. If you ever tell me that you are using the expanded algorithm and there's borrowing involved, you are incorrect. You are not using the expanded algorithm. I didn't mean expanded. I'm sorry, equal additions algorithm. That's not what it is. So how do we avoid borrowing? Well, let me show you. So I'd like for you to go ahead and write down the problem the same way that we did before. 834 minus 158 right on top of each other. And if you were doing this problem with the standard algorithm, the very first place you would need to borrow is in the ones place, correct? Yeah, I can't take 8 away from 4. It's the same problem I was working with before. That's not possible. But if that 8 were to become a 0, it'd be really nice, because subtracting 0 is really easy, right? Y'all with me? I can subtract 0 all day. Can you? You can. So how do I get the 8 to become a 0? Well, I add 2 to it. That'll do it, right? If I add 2 to my 8, it will become a 0. I mean, it's going to have more stuff in front of it, but the ones digit itself becomes a 0. But of course, if I add 2 to that number, I have to add 2 to the other number as well. Okay, so take a look at this. I've got 836 on top. That's cool. On bottom, I had 158, and I'm adding 2 to it. So what is 158 plus 2? 160. Now let's just look just at the ones place. 6 minus 0. Can you do that without borrowing? Yes, you can. Okay? So we're going to move one place value over. 3 minus 6. Can you do that without borrowing? No. So I need to do the same thing to it that I did to my 8. I need to add something to the lower value, which is a 6, to make it become 0. What do I have to add to 6 to get 0? 4. But it's in the tens place, so I need to add 40. But if I add it to the bottom number, I have to add it to the top number. So 836 plus 40 would be 876. And 160 plus 40 would be 200. So I already know I can do, 6 minus 0. I can do 7 minus 0. And I can do 8 minus 2, all without borrowing. So at the point when you can do the subtraction without borrowing, that's when you subtract. 6, 7, 6. So this is 676 without borrowing. So let's talk about for a second for why that one happens, and then we'll stop there today. So what's going on there? Well, it's happening because you have these two values, whatever they are, and they're unequal to begin with, right? I mean, they're not the same. And so what you're saying is that however far apart they are, if I raise them both the same amount, they're still that far apart, right? It would work too if I lowered them both by the same amount. But if I'm raising them both by the same amount, they're always that far apart. So this is the same idea. So I have one daughter who's like, she came out actually and she told me from the doctor's office that she was 5.5 feet, and I looked at her and I said, I think they told you 5 feet and half an inch. And she says, oh yeah, that is what they told me. Like, that's a little different than 5.5 feet. Anyway, so she's about 3 inches shorter than I am. But if we both put on 2-inch heels, we will still be the same difference in height that we are when we're standing flat-footed. Are you with me? Right? Like, this is the same as, I mean, that's what's happening in this problem. I can do this because I'm increasing both of them by the same amount every time I do that. And in doing so, it allows me to subtract without ever having to borrow. And that's the goal of equal additions algorithm. All right, so what we'll do next time is we'll move into adding and subtracting in other bases, and then some mental math.